Welcome to this explainer on mastering real numbers. Today, we're taking a topic that, let's be honest, usually feels like pure rote memorization, and we're turning it into a really fascinating logical journey. We're going to strip away all that complex jargon and just look at the pure mechanics of how numbers interact. By the time we wrap up, I promise you're going to see numbers and their relationships in a completely different light. So let's jump right in with a puzzle. Can you find the absolute largest number that divides 125, 162, and 259? But here's the catch. Leaves remainders of 5, 6, and 7, respectively. Now, if you try to brute force this, man, you'll be crunching numbers for hours. But as you'll see, by just grasping a few foundational rules, you're going to have a super simple two-step tool to solve this practically in your head. Here is our logical roadmap for this explainer. We'll start by demystifying HCF and LCM, then look at the prime factorization technique, the prime number rule, how to handle remainders in division, the zero-ending rule, and we will wrap it all up with the ultimate equation. All right, step 1, demystifying HCF and LCM. Before we even glance at any formulas or calculations, we've got to completely bypass those clunky textbook definitions and just get an intuitive feel for what these terms actually mean. Try to think of LCM and HCF not as abstract, boring acronyms, but as pure logical actions. The LCM, or least common multiple, is essentially looking upward. If you take the numbers 6 and 8, the LCM is the absolute smallest number that both 6 and 8 can divide into perfectly. So, in this case, 24. On the flip side, the HCF, highest common factor, well, that looks downward. It asks, okay, what's the absolutely largest number that can divide into both 6 and 8 perfectly? And here, that's just 2. Which brings us right to a golden rule of mathematics. Factor means remainder 0. Seriously, if a number is truly a factor of another number, it means it divides it completely. There is absolutely no remainder left behind. 0, nada. You'll want to lock this concept in your mind right now, because it is literally the secret key to solving that massive word problem we looked at a minute ago. Moving on to step 2, the prime factorization technique. Look, writing out massive multiplication tables to find common multiples is just exhausting. Nobody has time for that. Instead, there's this brilliant shortcut you can use by breaking numbers down to their absolute foundational building blocks, prime numbers. Let's compare 72 and 120 side by side. If we break 72 down into its prime ingredients, we get 2 to the power of 3 multiplied by 3 to the power of 2, right? Now for 120, we get 2 to the power of 3 times 3 to the power of 1 times 5 to the power of 1. So how on earth do we find the HCF from this? Well, it's actually incredibly simple. You just take what is common to both, and you take the lowest power. Since they both share a 2 to the power of 3, and they share a single 3, you just multiply those. Boom, your HCF is 24. But for the LCM, it's a bit different. We need a container big enough to hold everything. So we write down every unique prime number present across both. That's 2, 3, and 5. And we assign them their highest power. That gives us 2 cubed times 3 squared times 5, resulting in an LCM of 360. It is elegant, it's organized, and way, way faster than just guessing. Okay, step 3, the prime number rule. Let's run through a quick what-if scenario just to test our grasp on these core definitions. So, what exactly is the HCF and LCM of 2 prime numbers? Let's use 3 and 7 as a quick example. Take a second and think about the literal definition of a prime number. A prime number is only divisible by 1 in itself, right? That uniquely impacts its factors, doesn't it? And here is a vital shortcut rule that's going to save you so much time on tests. Because prime numbers only share the number 1 as a common factor, the highest common factor of any 2 prime numbers is always exactly 1, no exceptions. And because they share 0 other building blocks, their least common multiple is simply their product. 3 times 7 is 21. Done. If you see 2 prime numbers on a multiple choice question now, you literally can solve it in less than a second. Let's move to step 4, handling remainders in division. It is finally time to return to that complex word problem from the very beginning of the explainer. You remember our golden rule, right? Factor means remainder 0. Now, our original problem asks for a number that divides 125, 162, and 259, but leaves remainders of 5, 6, and 7. But wait, if there are remainders, we logically can't find an HCF yet because the division isn't perfect. So the crucial trick here is we just force it to be perfect.
Step 1. Subtract those given remainders from the original numbers. If 125 has a remainder of 5, just take the 5 away. You're left with 120. Do the same for the others. 162 minus 6 is 156. 259 minus 7 is 252. Okay, now for step 2. We just find the HCF of our brand new clean numbers 120, 156, and 252.
And the highest common factor of those three adjusted numbers is exactly 12. By simply subtracting the extra remainder first, we took what looked like an impossible paragraph and transformed it into a super basic, logical two-step deduction. Honestly, it's incredibly satisfying to realize you hold the power to manipulate the problem to fit your mathematical tools, isn't it?
Step 5. The zero ending rule. Let's tackle another common curveball you might see. Figuring out if a number with a massive exponent will ever end in a zero. For instance, think about the number 6 to the power of n, where n is literally any natural number. Will that ever end in a zero?
Well, this brings us to a completely non-negotiable law of mathematics. To end in zero, a prime factorization absolutely must contain both a 2 and a 5. Why? Because to end in a zero, a number has to be a multiple of 10, and the prime building blocks of 10 are exactly 2 and 5. If even one of those is missing, a zero is mathematically impossible. So let's apply that logic right back to the number 6. The prime factors of 6 are 2 and 3. So we have a 2, but no 5. If we do 6 to the power of 1, we just have 2 and 3. If we do 6 squared, we have 2 times 3 times 2 times 3, still no 5. You could literally take 6 to the power of 100. You just have a massive, endless string of 2s and 3s. No matter how many times you multiply that base, the number 5 is never going to magically appear. Therefore, 6 to the power of n can absolutely never end in the digit 0. It's brilliantly simple once you just break it down to those prime blocks. And finally, step 6, the ultimate equation. This is where we tie all these concepts together perfectly.
Consider this core principle for a second. The HCF is always a factor of the LCM. Because the HCF is built from the common lowest powers and the LCM is built from the highest inclusive powers, the HCF actually fits perfectly inside the LCM. Knowing this simple rule lets you instantly eliminate wrong answers on tests. Like if you're told the LCM of two numbers is 3600 and you're asked which multiple choice option could be the HCF and one of the options is 500, you know instantly it's wrong because 500 doesn't divide evenly into 3600. No actual math required, just pure logic.
This beautiful balance brings us to our final formula. For any two positive integers, let's call them a and b, the product of their HCF and LCM is exactly equal to the product of the two numbers themselves. The balance of mathematics here is honestly pretty elegant. The highest common factor multiplied by the least common multiple literally equals number a multiplied by number b. Which means if you know the HCF, the LCM, and just one of those original numbers, well, you now hold the exact algebraic key to unmasking that hidden second number. So the question is, can you apply this ultimate equation to unlock further mathematical mysteries on your own? I bet you can.